Welcome back to my class. In this series of lectures on network theory, we have already started gaining the fundamental concepts of circuit elements. We have already attended a class on passive elements and we have seen their different theories related to them, their various types, the various equations. Now in practical life, the electrical circuits or networks that we will be dealing with, those passive elements could be connected with each other in different ways. Now, series and parallel connections are two important connections among passive elements. So in this class we will be learning about these connections and if the passive elements are connected in series or parallel, then how we can simplify those networks and how we can finally obtain the response of the circuit, like voltage drop or current through any passive element. First I will start with series and parallel connection of resistances. Now in this diagram, as you can see here, we are having two resistors having their resistance value R1 and R2, and they are connected in some fashion. And how they are connected, one end of this R1 is connected with one end of R2 and other end of R1 is connected with the positive terminal of that voltage, and or we can say one terminal of that voltage source, and the other end of R2 is connected with the other terminal of that voltage source. That means one end of these two resistors are connected with each other at common point, and the other end of these two components or these two passive elements are connected to some other part of that electrical network. So this is series connection, and at this point no other component will be connected. Now the voltage source having value V has been connected with this series connection, and let's assume that this voltage source is supplying some current I. Across this resistor R1, the voltage which will be dropped is assumed as V1, and across this R2 the voltage drop has been assumed as V2. Now from inspection we can say that V will be equal to V1 plus V2. This equation or this relationship can also be proved by the help of Kirchhoff's voltage law, which will be discussed in some other class in this course. Since that has not yet been discussed, so we will take this concept for the time being and we will use this relationship. Now for resistors, we know that it obeys Ohm's law, and we know that as per Ohm's law the voltage drop across any resistor will be equal to the multiplication of the current value which is flowing through that resistor and the resistance value. So individually if we want to get their voltage drop value, then V1 can be written as I into R1 and V2 can be written as I into R2. In case of series connection of passive elements, the current which flows through that series connection is same. That's why in case of V1 and V2 the same current has been used, which is I here. Now if we assume that equivalent resistance of this series connection is R, then that will also obey Ohm's law, and in that case for the equivalent circuit the voltage which will be dropped across that equivalent circuit, that will be V. So it will look like as if we have a single resistor which has value R, and with that across that the same voltage has been is connected, that is V, and that is supplying the same current I. So this will also obey Ohm's law, and we can write V will be equal to I into R. Now in this equation, if we replace, if we put all these values of V1, V2 and V, what we can get here is in place of V, it will be I into R, and in place of V1 we can write I multiplied by R1, and it will be I into R2. Now here in both the sides of that equation, as we can see here, the current is same and that has non-zero value, so we can cancel that current value, which is the common factor or common term in this equation, from both the sides. So if we cancel that, what will remain in that simplified equation will be R will be equal to R1 plus R2. So we can say in case of series connection of resistors, the equivalent resistance will be equal to the summation of their individual resistance value. So here we work with two resistors only. So here R is equal to R1 plus R2. Now next we will see the parallel connection between two resistors. Here this resistor R1 and R2, they are connected in some fashion, and how it is, one end of R1 is connected with one end of R2 and the other end of R1 is connected with the other end of R2. So here both the ends of R1 R2 are common. So between this point and between this point, the two resistors are connected, and again between those 2 points the voltage, the supply voltage has been connected. So here we can see that the voltage drop or voltage value across each component in that parallel connection is same. So in case of series connection, as we have seen, the current value is same through every component in that series connection, and in case of parallel connection, voltage value is same across every component in that parallel connection. Now if we assume that this voltage source is supplying some current I, now this current I will be divided into two parts, I1 and I2. I1 is the current which flows through R1 and I2 flows through R2. Now again from inspection we can see, or we can say, that I will be equal to main current I is equal to the summation of their individual values. Now from Ohm's law, again we know that V will be equal to IR. So if we find out the individual current values, so I1 will be equal to, and if we assume that the equivalent resistance value of that parallel connection is R, then again it will obey Ohm's law, and this time we can write V will be equal to I into R. Now if we replace all these values of I1, I2 and I, then in this equation what we can write is V by R will be equal to V by R1 plus V by R2. Now since V is common on both the sides of that equation, which has again non-zero value, so that term will be vanished from both the sides, and what will remain finally in the modified equation is, and that will be 1 by R will be equal to 1 by R1 plus 1 by R2. And if we simplify further, then R will be equal to R1 multiplied by R2 divided by R1 plus R2. So this is the equivalent resistance value between of the parallel connection of two resistors. Next, we will simplify an electrical network which has multiple resistors and they are either connected in series or parallel, and we will find out the equivalent resistance value between these two terminals X and Y. Now if we assess this part of the circuit, then we can see here there's these two resistors are connected in parallel. Now if we assume that the equivalent resistance value of this parallel connection is R1, then it will obey this formula. So it will be R1 value, R1 this time it is the equivalent resistance value between these two resistors. So it will be 2 multiplied by 2 divided by 2 plus 2, that we have seen in this formula. So it will be 4 divided by 4, that means 1 ohm. Now if we evaluate this part of the circuit, then we can see here this all these three resistors are connected in parallel with each other. So if we take only this part, these two resistors, then we can first find out the equivalent resistance of them. Now if we assume that R2 is the equivalent resistance, then R2 can be written as, or can be found out as, 3 multiplied by 3 by 2, that means 1.5 ohm. And that means in place of this two resistors, we can think of a single resistor which is again connected in parallel with this third resistor, which has value 3 ohm. So since this 3 ohm resistor and the equivalent resistance of this parallel connection is again connected in parallel, so again that can be simplified, and this time if we assume that the equivalent resistance value is R3, then it can be found out as 1.5 multiplied by this resistance value, so it is 3. So in place of this we will have a single resistor having value 1 ohm, and in place of this we will be having a single resistor which will be having value 1 ohm. Now in this case, interestingly, we can see here that in this parallel connection both the resistors are having the same value 2 ohm, and the equivalent resistance value that we have found out is half of their each value. So we can, without even putting into the formula, we can easily say that in a parallel connection of resistors, if both the resistors having the same value, then the equivalent resistance value will be half of their value, each value. So now in the modified circuit, what we will have is we will have this resistor which we already had in our original circuit, that has the value 2 ohm, and in place of this parallel connection we can think of this 1 ohm resistance, 1 ohm, and in place of this we can think of again a single resistor which has the resistance value 1 ohm. And between xy we had another resistor which has the value 6 ohm. Now in this part, if we focus on this part of the circuit, we can see here that these three resistors are connected in series. So if we assume that the equivalent resistance value of this is connection is R4, then that value can be found out as 2 plus 1 plus 1. So it will be 4 ohm. Now we can think this simplified circuit as we have two resistors having value 4 ohm and 6 ohm respectively, and we can find out the equivalent resistance value. So between this x and y, if the equivalent resistance value, if we assume as R, then it can be found out as 4 multiplied by 6, 4 ohm. That means the equivalent resistance value of this resistive network between x and y is 2.4 ohm. So we can easily apply the concept of, or we can easily use the formula of series connection and parallel connection, and we can find out the equivalent resistance. But before that, we have to be very sure that whether the two resistors are connected in series or parallel, and the concept I have already discussed or explained how we can evaluate the series connection and parallel connection. Now next we will see the series and parallel connection between inductors. Now in this circuit diagram, we can see here these two inductors having their inductance values L1 and L2. They are connected in series, and this time the logic is same. And with that series connection, our supply voltage having value V has been connected here, and this voltage source, let's assume, is supplying some current I. Now across this inductor L1, the voltage drop is V1, and across this inductor L2, the voltage drop is V2. Now again, from inspection we can write that V is equal to V1 plus V2. Now from Faraday's law of electromagnetic induction, we know that the voltage drop across any inductor, that V is, and if we go by this individual voltage drop value, then we can write that V1 will be equal to its inductance value, which is L1, then di by dt, and V2 will be equal, these two inductors are connected in series, so their current value will be same, and that's why in both the equations, the current value has been taken as same, and that is I. Now if we assume that the equivalent inductance of that series connection is L, then it will also obey this equation. So we can write that the voltage drop across these 2 points across this series connection is V. So it can be written as V will be equal to L into. So here now, if we in this equation, if we put all the values of V, V1 and V2, so we can write here, in place of V, we can write L into di by dt, and in place of V1, we can write L1 di by dt, plus it will be L2 di by dt. And here again we can see that on both the sides of that equation, this di by dt, this term of this factor is common, and which has non-zero value, so they will cancel each other, and in the modified equation what will remain is L will be equal to L1 plus L2. That means in case of a series connection between two inductors, the equivalent inductance is summation of their individual inductance values. So L is equal to L1 plus L2. Now next we will move to the parallel connection of inductors. Let's again assume that this voltage source is supplying some current I, And this time, since these two inductors are connected in parallel, so voltage drop across each inductor with across that parallel connection will be same. And this time the voltage drop across each inductor will be V. And here the current that will be flowing through each inductor will be different. Voltage will be same, but the current values will be different. So this main current at this point will be divided into two parts. I1 is the current which will be flowing through this the first inductor as having value inductance value L1, and I2 will be flowing through the second inductor. Now from inspection we can write that I will be equal to I1 plus I2. So main current will be equal to the summation of their individual current values. Now again it will obey the same Faraday's law. So V can be written as L into di dt. And from this equation we can if we want to express I in terms of voltage, then we can rearrange the terms this way, or we can modify this way. So it can be written as L into di will be equal to V into dt. Now we can further write that di will be 1 by L and then multiplied by V into dt. Now if we integrate both the sides, then integration of di can be written as I, and 1 by L is constant with respect to time. So we can take that factor, that constant term out of the integration. So 1 by L integration of V dt. Here voltage is a function of time, since here we are using an AC circuit having AC component like inductors. Now if we find out the individual current values, then I1 can be written as, now if we assume that the equivalent inductance of that parallel connection is L, then that will also obey this equation, or this equation. So we can write that for that parallel, the equivalent circuit, the main current will be I. So it can be written as I will be equal to 1 by the equivalent inductance, then integration of V dt, and this time the same voltage. So it will be same value V will be used. Now if we replace all the values of I1, I2 and I in this equation, so on the left side we can write 1 by L integration of V dt, and on the right side we can write, in place of I1 we can write this 1 by L1 integration of V dt plus, and then in place of I2 we can write this. So it will be 1 by L2 integration of V dt. So in this equation we can notice here that this integration of V dt is common factor, and that also has some non-zero value. So we can cancel that factor from both the sides. So what will remain in our modified equation is 1 by L, and that will be equal to 1 by L1 plus 1 by L2. Now if we simplify further, then L will be equal to L1 multiplied by L2 divided by L1 plus L2. So this is the formula of equivalent inductance when two inductors are connected in parallel. Now if we have more than two inductors, then we can simplify step by step. So we will take one combination of one parallel combination of two inductors. Then with that simplified inductor, we can take the parallel connection of the third inductor, and if we have few more, then step by step we can further simplify by using this formula. Now next we will see another electrical network where we have only inductors, and we this time we want to find out the current value through 4 Henry inductor, that means through this inductor. So here what we can see is between this point X and Y we have 4 inductors, and between A and B these two inductors are connected in series, and with that series connection this inductor is connected in parallel from the same logic. And with this connection this 3 Henry inductor is connected again in series, and with that whole connection of these 4 inductors this 10 ampere current source is connected in parallel. Now let's proceed step by step. So first evaluate this series connection of these two inductors. Now if we assume that the equivalent inductance value is L1 of this series connection, then As we know that equivalent inductance will be summation of their individual values. So equivalent inductance of this series connection will be nothing but 2 plus 2. So it will be simply 4 Henry. Now in place of this series connection, we can assume as if we have a single inductor having 4 Henry, and with that series connection we have again another inductor that also has 4 Henry value. So if we simplify further and if we assume that of that parallel connection the equivalent inductance is L2, then it will obey this formula. So it will be multiplication of the individual values divided by summation of their individual values. So L2 will be 4 this inductor, then this 4. So 4 multiplied by 4 divided by 4 plus 4. So it will be 16 by 8. So 2 Henry. Now, one thing we can notice here that of this series connection, the equivalent inductance value was 4 Henry, and of this inductor also the inductance value is 4 Henry. So in this parallel connection, both the inductors are having the same inductance value, which is 4 Henry, and of their equivalent inductance, that value is 2 Henry. So that means if in a parallel connection, the inductors, if we have two inductors and they are having the same value, then the equivalent inductance value will be half of their each value. So this time it is 2 Henry. Now what we can in the modified circuit, what we will have is the 3 Henry inductor which we had in our original circuit, and for this, instead of this connection, we will have an inductor that will have value 2 Henry, and with that this is X and this is Y terminal, and with that we are having a current source which has current 10 ampere. So this 10 ampere current, now this time in this modified circuit we can say that these two inductors are connected in series, and with that this current source is also connected in series. So this 10 ampere current will be flowing through each of these inductors. So through this 3 Henry inductor and also 2 Henry inductor, which is the equivalence of this whole circuit. So this through 2 Henry inductor also, this 10 ampere current will be flowing. Now where from this 2 Henry came, this is the equivalent inductance between these two parallel paths. So initially we solved this series connection and then we solved the parallel connection. So we can say that at this point A, this 10 ampere main current will be divided, actually in the original circuit will be divided into two parts. One part will be flowing through this 4 Henry and another part will be flowing through this path, which instead of these two inductances, we can think of a single inductor having value 4 Henry here. So we can here, now we can apply, since here the current is getting divided into two parts, so we can apply the current division rule. So if we want to find out the current value through this inductor, then that current value will be equal to the inductance value of the other inductor, and this time the equivalent inductance value is 4 Henry. So 4 divided by 4 plus 4 into the main current, which is 10 ampere. So it will be 1 by 2 into 10 ampere. So it will be 5 ampere. And again, one thing we can notice here, that in the parallel connection, for this series connection, we have one inductor that has value 4 Henry, and for this inductor we again had one inductor which also has 4 Henry, and here we had this inductor which has the value 3 Henry. So through this also 10 ampere current is flowing, and this 10 ampere current is getting divided into two parts, and we are focusing on the current which is flowing through this inductor. So here we can see that in this parallel connection both the inductors having the same value. So through each one of them the current that will be flowing will be half of the main current value. So that's why since the main current value is 10 ampere, so through each of this parallel path, the current which will be flowing is 5 ampere. So If both the inductors or both the passive elements are having the same value, then without even using the formula, we can say that the current value. And this time the current which will be flowing through this 4 Henry inductor, this value is 5 ampere. Now next we will see the series and parallel connection between capacitors. So in this diagram what we can see is these two capacitors having capacitance value C1 and C2, they are connected in series, and we can also explain the series connection from the same concept, same logic. And with that series connection, this voltage source having value V is connected, and this voltage source, let's assume again the current which is supplying is I, and V1 and V2 are the voltage drop across these two capacitors respectively. Now in case of capacitor, we know that the current value I which flows through a particular capacitor, that is equal to C, the capacitance value of that capacitor, into dV by dt, where V is the voltage drop across that capacitor. So if we individually find out their voltage value, then we can, what we can do is uh, from here we can first express the voltage in terms of current. So we can rearrange the terms this way: C into dV, and that can be written as I into dt, cross multiplication. So now we can write as dV will be equal to 1 by C I dt. Here I is also a function of time. So now if we integrate both the sides of this equation, so integration of dV will give us V, and here 1 by C is again constant, so it will be taken out of this integration, and it will be integration of I dt. Now if we find out the individual voltage drop, so it can be found out this way: V1 will be 1 by C1, the its capacitance value. So V1 is the voltage drop across this capacitor, so its capacitance value 1 by C1, and I dt. And since these two capacitors are connected in series, so their current values will be same. Now if we assume that the equivalent capacitance of this series connection is C, then of that equivalent circuit, the voltage will be, again the voltage value will be same. It will look like as if there is only single capacitor and there is this voltage source between these 2 points. So these 2 points means these 2 points, say if it is X, if we assume that X, and this as Y, then X and Y. So again this equivalent capacitor that will obey this formula, or we can say this formula. So if we want to find out in terms of the voltage value, the supply voltage value or main voltage value, then it can be written as V, and this time we will be using the equivalent capacitance. So this will be 1 by C, and then I dt, the main current, so it will be I. Now from inspection we can write again the same thing: V will be equal to the main voltage, supply voltage will be equal to summation of their individual voltage drops across each passive element. Now if we replace V by 1 by C I dt, and accordingly V1 and V2, we can notice one thing, that integration of I dt is the common factor on both the sides of that equation, and which has again has some non-zero value, so we can cancel that terms. What will remain in the modified equation is 1 by C will be equal to 1 by C1 plus 1 by C2. So if we simplify further, then C will be equal to C1 multiplied by C2 divided by C1 plus C2. So here the equivalent capacitance value of a series connection between two capacitors is this, and this pattern or this formula is same as the parallel connection between resistors or parallel connection between inductors. So this time in case of capacitor is the opposite. Now we'll go to the parallel connection of two capacitors. Now in this circuit diagram, what we can see is these two capacitors having capacitance value C1 and C2, they are connected in parallel, and with that parallel connection, again the voltage source having value V is connected, and this voltage source is supplying some current I, And since this is a parallel connection, so the voltage drop across each of this capacitor or across that parallel connection will be same. So across this capacitor C1 and C2, the voltage value will be V, and this time current value that will be flowing through each of them will be different. So here the main current I will be divided into two parts here, and I1 will be flowing through C1 and I2 will be flowing through C2. Now it will obey the same formula. I will be equal to C dV dt. This is the relationship between I and V in case of capacitor. So here individually, if we found out the values, individual values, then it will be I1 will be equal to C1 dV by dt, and I2, the second current flowing through the second capacitor, it will be C2 into dV by dt. And since this time they are connected in parallel, so voltage value will be same. Now, if we assume that C is the equivalent capacitance of this parallel connection, then it will again can be written as I will be equal to, for the equivalent circuit, the main current will be used. So it will be IC into dV dt. Now from inspection we can say the main current I will be equal to I1 plus I2, summation of their individual current values. So in place of I we can write C into dV by dt, and in place of I1 C1 dV by dt plus C2 dV by dt. Now here we can see that dV by dt, this factor is common. So we can cancel that factor, and what will remain in the final equation is C will be equal to C1 plus C2. So in case of parallel connection between two capacitors, the equivalent capacitance will be simply summation of their individual capacitors value, and again this time it matches with the formula of series connection between resistors and inductors. So this time again in case of capacitor it is opposite. Now next we will see a network, electrical network, which has only capacitors, and they are either connected in series or parallel, and with the between this A and C, and with that network a voltage source having value 15 volt is connected. And what is expected from us to find out the voltage drop across 2 farad capacitors. So in this circuit we have this 2 farad capacitor, twice 2 farad capacitors. So across this capacitor we have to find out the voltage drop. So for that we have to simplify this circuit step by step. So if we evaluate this part of the circuit, then we can see here these two capacitors are connected in parallel. So if we assume that the equivalent capacitance value is C1 for this parallel connection, then it will be simply, for parallel connection it is simply summation of their individual values. So it will be 2.5 plus 2.5. Unit of capacitance is farad. Now if we assess this part of the circuit, then we can see here these two capacitors are connected in series. So if we assume the equivalent capacitance value is C2, then it will be this formula. So multiplication of their individual values, so it will be 2 multiplied by 2 divided by summation of their individual values, so it will be 1 farad. That means in this part now we will have 3 capacitors. This will have 1 farad, and the equivalent capacitor will have value 1 farad, and this has 3 farad. So if we take, if we assume the equivalent capacitance value as C3, so then the C3 can be found out as, it will be summation of their individual values. So 1 plus 1 plus 3. So it will be 4 plus 1, 5 farad. Now this has, we can redraw the simplified circuit as this one single capacitor, here one single capacitor. So this is between A and C, and in between we have the point B. Now this capacitor is the equivalent capacitance of this connection, and that has value 5 farad. And this capacitor is the equivalent capacitor of this connection, and that has also value 5 farad, that we have already found out here. Now with that we have another capacitor which also has value 5 farad. Now what we have to find out, the voltage drop across each of these 2 farad capacitors. So since in case of parallel connection we know the voltage value is same, so we can say that across this 5 farad capacitor the voltage drop will be 15 volt, and between this AC the voltage drop will be again 15 volts. So first we will find out AB, because these 2 farad capacitors, they are connected in between AB only. So first we will find out the voltage drop across this 5 farad capacitor between these 2 points AB. Now for this we will obey the voltage division rule. We'll follow that. Now in case of voltage division rule, we know that if we want to find out the voltage drop across AB, then it will be that capacitor value 5 farad and divided by their individual capacitance values 5 plus 5. Though in case of AC component in like inductor and capacitor, directly the current is a voltage value uh, is not found out by using their inductance or capacitance value in place, or rather it is voltage drop across, suppose if it is capacitor, then voltage drop across capacitor is the current value into its reactance value. So it will be XC, V will be I into XC, and in case of it is capacitive reactance, and in case of inductive circuit it will V will be equal to I into XL. This is inductive reactance. And we know that capacitive reactance, it is 1 by omega C, where omega is equal to 1 by 2 pi f into L, where small f is the linear frequency of the supply. But if we take the ratio of their current values or voltage values, then finally it will be the ratio of their individual capacitance, and can be expressed as the ratio of their individual capacitance and inductance value, as this 2 pi f is the constant factor, because 2 pi is constant and f is the supply frequency which remains constant. So that's why in case of voltage division rule or current division rule, in case of inductor or capacitor, we can directly use their in the ratio, we can directly use their inductance or capacitance value. Likewise we use in case of resistive circuit. So here it will be the capacitance value of this capacitor, which is 5, divided by their individual summation of their individual capacitances. So 5 plus 5, and then the main voltage, which is 15 volt. This formula we have already seen in other class in case of resistive circuit. So it will be half into 15, so it will be 7.5 volt. And interestingly, we can notice here then these two capacitors, they are having the same value, 5 farad each, and their main voltage across these 2 points is 15 volts. So since they are having the same value, so across each capacitor the voltage which will be dropped will be half of the main voltage. So that's why it is 7.5. So without using the concept of voltage division rule, the formula of voltage division rule, we can directly find out, or we can directly say that how much will be the voltage drop across each capacitor if both of them are having the same value, whatever is the value is. Now our main focus is the concern is to find out the voltage drop across each 2 farad capacitor. So here since between A, B, again these two capacitors are connected, so again we can find out, we can apply the concept of voltage division rule. Now suppose if we want to find out VAD, so we can apply the same formula. So this time it will be 2 divided by 2 plus 2, and then 7.5. So it will be again half of 7.5, so it will be 3. And by using the same concept we can find out the voltage drop across this capacitor also. And again, since this time in this series connection each capacitor has the same value, so again without using this formula we can say that across AB the voltage drop is 7.5, and since these two capacitors are having the same value, so across each capacitor the half of their main half of this voltage will be dropped. So this time it will be 3.75. So this is the way how we can use the concept of series connection and parallel connection between every passive element, be it resistor, capacitor, or inductor, and we can simplify a given electrical network. So with this, I end today's class.